let's try to look at this advection operator. So in fact, this equation, when you just have the advection operator, is called the free transport equation. Now I'm looking at angles, okay, instead of x, so they are between 0 and 2 pi, but omega is still going minus infinity to plus infinity, okay? And now I want to look, how does this look? Because we know that it has a natural continuous spectrum, okay? So remember, we studied in the first lecture the harmonic oscillator case, where we had also natural eigenvalues, but here we have only two, okay? Remember? And here we have a whole line of continuous spectrum, okay? So basically, here we had oscillation, our system was oscillating, and here what is it gonna do? What is it gonna do? Yeah, that's the question. Also, another thing, here the solution, we could decompose it in terms of eigenvectors with the exponential of the eigenvalue in time, okay? And we had true eigenvectors. Now, I'm not showing this, but one can show that we could decompose the f in terms of integral of the spectrum, because here you have a sum because you have just two eigenvectors. Here you have a whole line, so you have to integrate over d lambda, in fact. Okay. Yeah. So. And the psi that are like the eigenvectors, they are not eigenvectors because as we saw, they are like kind of delta function, or here it's not really delta function, but they do not belong to the space L2. So that's the difference between the two. Now let's go and look at this equation. Okay. So to look at this equation, example that I like is imagine that F is a density of people that are running a marathon. So they are running a marathon on a track, okay? So theta is the angle they are at. So here theta equals 0, here theta equals pi, etc. Okay? So, and omega is their speed, okay? So they have all a different speed, and I distribute this speed according to this J function. So in fact, if you remember the Kuramoto model, it is like the frequency of the oscillator, and theta is their phase. So now my initial condition is that they are all, so this delta function means that they are all here at this angle theta. So they all start at the same point, okay? So now we'll see, let them run and see what happened. So here, remember that each runner run at a constant speed given by its omega, okay? So if I let the system evolve, then the one, here I put the one that run the faster at the right, and the one that run the lower at the left, okay? So basically, as we could expect, the one that run faster are in front of the other, okay? So if you let the system evolve, you see this line is kind of stretching, okay? So this you can kind of expect, okay? And then the one that are in the first, the top runner, basically he already has a turn on the other, okay? Now if I let run them for a very long time, that's why I say it's a marathon, then at some point you have this kind of filaments of people running that create, okay? And if I let run them again longer, I have this, and then at some point I cannot distinguish any filament, okay? So this is called filamentation, okay? And you see that the end state, if I let them run for forever, basically my finite state, which is also a steady state, will be, in some sense, will be that they have no dependence over the angle, they are equally distributed, they're homogenized, as we say, and just they have the distribution over the velocity. So now if you remember the Kuramoto case, the steady state of Kuramoto was exactly this quantity. So basically the phenomenon, what did happen here with this one? We had mixing and filamentation, and basically it's the same phenomena when you mix milk into coffee, you mix, and then at some point you cannot see the milk anymore. Okay? And that's what happened here. The final state, as I said, is the same but the Kuramoto model. Okay? Any initial state, or almost any initial state, the ones that are regular enough, let's say, they will relax to this state. Relax means that they go toward this state. So it is a damping phenomena in a sense, because I start from some state here and I always converge to this state here. Okay? So it is kind of damping. I remember the damped harmonic oscillator. We always converge to the 0, 0 state. Here, we always converge to this state, but without any eigenvalue that has a negative real part. So it's really the effect of the continuous spectrum. The effect of this guy is to mix your system so that it relaxes to this state, okay? But, yeah, the speed of this process depends only on the regularity. So if J is a continuous function, have continuous derivative, etc., on the J function, okay? And what is amazing, and that some people when this phenomena was kind of discovered, were skeptical about, is that this conserves the energy, the entropy, etc. So it means we keep all the information in the system. So it's very different from a damping that happens when lambda is negative, okay? Here it's really a neutral damping. It's just a mixing, but all the information is kept. While in general, when you have dissipative process, like the damping of the pendulum, you lost some information, okay? And one very good example to see that is example here in a fluid example. So here I'm not saying it is exactly the same thing, but I think the conceptually it's very, very similar. So basically here they put in a fluid that is very viscous, they put colorant, okay? And so they put two different colorants, you see, green and red. And then they will, okay, they put the blue one also. Okay. And then they start to mix the system. So here they do it slowly, because if they do it too fast, then they will have some real damping, some real loss of information. Okay? So here they just mix the system as you could mix milk and coffee or other stuff. Okay? But they do it sufficiently slow that you can imagine it is just the continuous, natural continuous spectrum that acts. Okay? So now they mix it very well. It like the marathon before, you cannot distinguish any color. And now they just run back the marathon in the other direction. Okay? You see, they turn this in the other direction. And the idea is of this mixing is that because there is no loss of information, you should recover your initial state. So now let's see if that's work. So you see that works. So they exactly end up with almost the same initial state. So meaning that it is indeed like a neutral mixing. So it is and not a real damping. Now, yeah. Now let's get back to this this full operator with the advection term and the interaction term of the oscillators. Okay, and here in this context, the mixing phenomena is known as Landau damping, basically. So it was discovered in the context of plasma physics, because in plasma physics you have electrons, they have different speed, so they mix, but yeah. Then you have many more subtleties, but let's say the basis of the phenomena of Landau damping is just this mixing with a continuous spectrum. Okay, but yeah, I'm not saying that's all the story, but that's most of the story. So now let's get back to really the end of the talk, which is how the synchronization happens. So we saw that for some coupling, if the coupling is too weak, okay, it is below some Kc, then there is just this continuous spectrum. And basically it means that the mixing is stronger than the coupling. Then, so below Kc, the only steady state possible is R equals 0. Remember, R was measuring the synchrony. So when R is 0, it means that the system is not synchronized. So it's all mixed. Okay? And here. Now, if I increase K, what happens is that if I increase K, R equals 0 is no longer steady state, but is stable. Okay? Or neutrally stable, as we say, because as I said, it's not really stable because there is no eigenvalue here. Okay, it is neutrally stable. That's the term. And now it will become unstable because there will be some eigenvalue here that has positive real part. There is also one here, but does not do much to the dynamics that appear here. And you can find it with some kind of dispersion relation, as in the previous, remember the example where we had already encountered this type of dispersion relation. We can derive one for the Kuramoto case, and this, basically for K large enough, you can find that there is some eigenvalues. And yeah. And in this case, it means that my zero state here becomes unstable, and then it's go away from this state, and then it find a new steady state that is here. Okay, so now you might ask, but how can we predict this line? So in this case, you have to study this continuous spectrum plus unstable eigenvalues, and I'm telling you that it is not straightforward, and it is not simple, because now you have a linear dynamics when you go away from your. So I was saying that to predict this line, basically you have to know the eigenvalue with that. So you know there is a continuous spectrum, and for a given K, you know that your linear dynamics tells you, the instability tells you that you will go away exponentially. You will go away exponentially fast, and then the nonlinear terms of your equation won't be small, and they start to increase. So then it will stop your instability at some point here. So it means that in this case, you have to use nonlinear tools. So this is absolutely not the focus of today, but basically you will have to find to do nonlinear analysis. So this is the final slide. What did we learn, or what did I talk about? Basically, dynamical system. An idea that I find nice is that they simply describe apparently complex phenomena. Like we saw that they can simply, with a few terms, you can simply model evolution of population of prey and predators. You can also have intuition about the wage share and the relation with the employment rates. You can then modify your system so it is more complex and maybe more realistic, and then you have a dynamics which is more complex. And then when you want to study this system, you use in general spectral analysis. It is very useful. It does not do everything, sorry, because spectral analysis is related to linear dynamics, and there is also the nonlinear dynamics which can do things. Okay, so spectral analysis, we saw it also exists the definitions in infinite dimension. And basically, it brings the continuous spectrum, the residual spectrum. Here, I focus on what the continuous spectrum was doing. In particular, with the neutral continuous spectrum, seems to mix the systems, and we can use that to study PDE. So as I show that when you have a very large number dynamical system with a large number of ODE, okay, basically it is too much to study, and you cannot do much thing except do numerics. So if you want analytical results, if you want a deep understanding with a theoretical result, what you can do is describe a population with a density description. So you use a function that describes the density of the system, and basically how this density will evolve in time, it will be given by a partial differential equation. And then we can study this PDE with the spectral analysis. And basically, with all that, we had all the tools to study very briefly, of course, and on the surface, the synchronization phenomena. And the main takeaway is that the synchronization, it is always a battle between mixing, as you saw in the video with the colors or the fluids, or the marathon running. It's always it's a battle between mixing and coupling. Okay. So it means that when one is stronger, you will have, when mixing is stronger, your system will be homogenized. So it means you won't have synchrony. And then the coupling is strong enough, you can study the linear dynamic and then nonlinear dynamics and predict what type of synchrony you will have, how much your system will synchronize. So, for example, yeah. So next time you are in a crowd and all people start to clap, you can try to listen that at the beginning, if it's a nice crowd, of course. At the beginning, people will tend to be desynchronized when they clap, and at some point, they'll start to synchronize, which means that in this crowd, the desynchronized state is not stable, because you go away from desynchronized to have synchronization. That's it. So if you have questions, yeah, you don't hesitate, please send them to me, and thank you for listening. Bye.